Start. Okay, so let's start. Good morning. So today I'll be discussing more about dust and molecules in the interstellar medium. So here you can see the background picture, which is known as the pillars of creation. So these are gaseous clouds containing molecules, dust particles, and a lot of things. A lot of beautiful chemistry is going on, which is very difficult to reproduce in labs on the earth. And these are known as pillars of creation. Why? Because a lot of star formation activity goes on. I mean, the red dots that you see are all young stars that are being formed in these pillars of creation. So just to start with the electromagnetic spectrum. So what you can see here is what reaches to us on the earth. So we have a telescope which works in the visible part of the electromagnetic spectrum. So that reaches us on the earth, so we can do photometry and spectroscopy on using telescopes on Earth. And the radio part of the electromagnetic spectrum from the cosmos can reach us on the Earth. But we see a big gap here. This is very useful for us. Why? Because we don't want gamma rays, X-rays, and high energy photons reaching us because we won't survive. So in order to do astronomy in this part of the electromagnetic spectrum, we have to go to space. And then IR, we have some windows. Some part of the spectrum reaches us, but most of it doesn't. So again, we need satellite-based telescope which can fly and go above the Earth's atmosphere, and we can do astronomy using this. And so here, because I'm going to discuss more about dust and molecules. So yesterday, like I gave an example of O6 spectrum, which was in the far ultraviolet. Here will be mostly restricted to the IR phase, because molecules are mostly detected using IR and radio, mostly radio, but some IR as well. So yesterday we already talked about the interstellar medium, and we know that the space between stars is not empty. It contains a lot of material, solid particles, gases, particles, atoms, ions, molecules, a lot of things. So galaxy, if you can see, galaxy has a lot of stars, dark matter, plus interstellar gas and dust. And already I have told you yesterday that the interstellar medium, the interstellar gas, and the particles, they play a very important role in star formation and evolution of galaxies. So this all we have already discussed. The interstellar medium matter that exists between stars. This can include gas and particles. Gas mostly in ionic, atomic, and molecular form. And there is a lot of energy. This energy comes basically from this radiation coming from the stars. So it is known as interstellar radiation field, and this affects all the material that is in the interstellar medium. Okay, so this can ionize the material. This can cause reactions, and so it is very helpful. The interstellar radiation field can destroy molecules. So again, the cycle, of the material that is found in the interstellar medium. So if we start from here, we have a gaseous cloud from where star and planet formation can take place, and because it has molecules, and most of the molecules that have been detected in space are organic in nature, they are carbon based, and our life is also carbon based. So it may be that the origin of life has something coming from the interstellar medium. After the star formation, the star evolves as life goes on. The star can take different routes, depending on the size and mass of the star. So it will definitely form a red giant or a supergiant, and then it can follow this path. For example, our sun will be following this path. and it will form a white dwarf and a planetary nebula. This planetary nebula will be moving away from the star and it will again merge in the stellar medium. While the massive stars, they will follow this path, they will blast off as a supernova, and they will be releasing a lot of heavier elements in the interstellar medium again. So all the heavier elements will go again and be part of the interstellar medium, and the star will form either neutron star or black hole. Yes.
AGB stars. What does AGB?
AGB are asymptotic giant branch stars. So if you have already learned about the HR diagram, okay, so we have the main sequence stars going like this. Then we have a branching out from the main sequence. When the star evolves means all of the fuel, the hydrogen which was burning is over. So now it will leave the main sequence, and it will be like a asymptote, and it will expand in size. So AGBs are basically lake type stars, and they are very, very important. Why? Because their outer envelope is like leaving the star. Okay, so it is cooling and it is quite dense also. So when the temperature reaches like 1000, 2000 Kelvin, then the material which is there, the atoms, the ion, they can react. They can start some chemical reaction, and molecule formation can take place. So that is why AGB stars, they are also known as late type stars. They play a very important role in the formation of molecules. Sorry. So you can see, we have already discussed interstellar clouds. We know about diffuse and dense and translucent clouds. So you can see the dark patches. All the bright things are stars, and the dark patches are clouds, which are hiding stars behind them. Okay, so they are not allowing the light from the stars to come to us. But this is visible part of the spectrum. We can see the light, their light maybe in a different part of the electromagnetic spectrum. Okay, so we many kinds of so all these clouds are known as nebulae, and nebulae, we can have emission, reflection, dark, nebulae kind of thing. I will show you pictures. So here you see a dark patch. This is a field where you can see a lot of stars, maybe galaxies in the background, and we see a dark patch. So people started wondering why there's a dark patch. Maybe there is a hole in the sky. There's nothing in the dark patch. But then if you switch your telescope to infrared wavelengths, you start seeing the background objects in this dark patch. That means this dark patch is nothing but a gaseous cloud, which is not allowing the background light some part of the background light, it is absorbing all the light. Okay, and then that absorbed light may be re-radiated at longer wavelengths. So if we switch our telescopes to longer wavelengths, then we'll be able to see those background sources. Okay, so this clearly indicates the presence of a very dense cloud which is hiding the background stars. Again, the pillars of creation already told you about. So you can see, how star formation activity is taking place. These are very dense and these are huge objects, several hundred light years across. They are very giant molecular clouds. A lot of beautiful chemistry is going on. This okay, so this is a reflection nebula. So reflection nebula is a nebula that is reflecting the light, reflecting star light towards us. Okay, so reflection nebula basically are very exposed to the high energy photons coming from the stars. Okay, so they are, you can say that they are very tenuous and they are highly exposed. So their environment is very it's not easy for molecules to survive there because they are so exposed. Then we have planetary nebula. So planetary nebula is like when our sun will use up all its fuel, then it will go to the stage. So at the center, this white thing is the white dwarf which is being formed, and all this envelope is going away from the object. Okay, so because the white dwarf is extremely hot, it is like 100,000 Kelvin or something like that. So you can see that the planetary nebula is shining with that light, okay, and it is going away from the object. And then slowly it moves away and away, and when it moves away, then a lot of activities can go on in this nebula actually, because the temperature and the conditions will be so favorable for chemical reactions to go on. So a lot of molecule formation can take place in planetary nebula kind of objects. So diffuse, we've already talked about diffuse interstellar gas. Diffuse interstellar gas, the density is less, so high energy UV photons can reach in the diffuse interstellar gas. So we mostly use spectroscopy for detection of species of material in the interstellar medium. And spectroscopy is something like this. We have light that has to break into the various wavelengths. This is an crude way of doing spectroscopy, but the more sophisticated way is using telescopes. They use gratings. So gratings, the resolution will be much higher. Okay, and we need high resolution spectroscopy because we need to separate lines. So if suppose there is a line at 1000 angstrom, there's another line at 1001 angstrom. So we need to separate that. So it is having a difference of only 1 angstrom. So the resolution of our spectrometer should be so high that we are able to resolve the line at 1000 angstrom, then 1001 angstrom. The spectrometers that we use in our BSc labs, you can see, so sodium lines we can easily resolve, but the separation is about 6 angstroms. So they are also quite good actually. They are able to resolve the 6 angstrom thing, but we need even higher resolution, higher signal to noise, so that we can do, because the lines will be very crowded. Certain regions they are very crowded, so we want them to be separated. So this already we have seen that there can be a redshift and blue shift. All the elements they have their own spectral lines, so that is the way we can actually identify these elements. So here, how do we know that the lines are coming? Yesterday there was also a question. How do we know that the lines are coming from the interstellar media and not from the star? So if we have a binary system, the atmosphere of the binary stars will also have absorption lines, and then we have this cloud, which again gives rise to some absorption lines. But lines due to the binary system will be, they will be moving. So they will either be red shifted or they will be blue shifted. So, and the lines coming from the cloud will be stationary. So this is the way to identify these kind of, the lines which are coming from interstellar medium, the lines which are part of the solar system. So in this way we can identify the lines, and then we can identify the material that is present in the interstellar cloud. Okay, so this is another example where you can say that where you can see the light from star A is passing through two different clouds. And from star B, it is passing through only one cloud. So you get one dip for star B, and you get two dips for star A, which I also showed yesterday the example in the example. And you can see that these clouds are moving towards the telescope. That means there will be a blue shift. You can see that there will be a blue shift. So it is blue shifted. The line is here. For star A, it is this side, and the local, this one is local. So star B, the cloud, this cloud, the green one is this cloud, the blue one is this cloud. Okay. Yesterday, in yesterday's example, we saw that the local, the Milky Way was here, and the LMC was shifted here. Okay, that means it had a red shift. This one is blue shift because it has a the radial velocity is minus kind of 100 because it is moving towards the telescope. And in yesterday's example, we saw that it was not moving towards, it was moving away. Okay, so it had a red shift. Here we see an example of blue shift. Okay, so in this manner, we can actually, and sometimes what happens when these clouds are too close to each other, then these lines will overlap. But then we will have to identify how many clouds. There can be 2 clouds, 3 clouds, several clouds, 5 clouds. So we will have to identify how many clouds this starlight is passing through. Okay, and this can be done using, you have to fit these spectral lines. So you can use the most simple one is say Gaussian fit. You can fit it with a Gaussian curve, and then you can measure the area of the curve, and then you can find the equivalent width and column density and so on. And you have to do it for all the individual clouds. Okay, so 21 centimeter line already know about. So hydrogen is the most abundant element in this universe, and identification of hydrogen atom, atomic hydrogen, is done by using its 21 centimeter line, which can be identified using a radio telescope at looking at 1420 megahertz, which is the NCRA, the GMRT works in this wavelength. So what happens is hydrogen atom has a proton and an electron. If so, proton and electron can have spins in the same direction or in the opposite direction. When they have spin in the same direction, that is more energetic compared to the spins in opposite direction. So this one has very slightly higher energy. So that means the spin has to flip. So the electron spin flips down to come to the ground state, and when it flips down, it releases some photons. So those photons lie at 21 centimeter. Now this flipping is not allowed spectroscopy. Okay? If select, there are selection rules in spectroscopy which doesn't allow this spin flipping. So that means the spin flipping will be very, very slow. So every about 100 million years it takes for the spin to flip. But then how do we see? How do we see so much of hydrogen if it takes so much time? Because the number of hydrogen atoms is so large, it is huge. So if this and we are way ahead from the Big Bang era, and a lot of hydrogen has been formed, and we are so much ahead. So if some spin flipping is taking place, the photons are reaching us now. So a lot of hydrogen can be detected using this spin flip. And first detection was done in 1951. So this is an all-sky map of 21 centimeter line. And you can see a lot of hydrogen in this. This is our Milky Way. So you can see a lot of neutral hydrogen, and all the bright red things are hydrogen. Dark ones are less hydrogen. So you can see as we go away from the center of the galaxy, we move away. We see that the amount of hydrogen. The amount of hydrogen, neutral hydrogen, also indicates the presence of gas and dust, because ultimately the gas and dust formation will take place. I mean, the material which will be ejected from the stars. So stars will be formed from this neutral hydrogen, and the nuclear fusion reactions will go on, and it will produce heavier elements, and those elements will come out of the stars, and then they will react. So it is somewhat proportional. So you will see where you will see more hydrogen, there only you will find more amount of molecules and dust particles. So just a comparison, you can see that diffuse interstellar medium, it is about 1 particle per centimeter cube, while on Earth it is about 10 to the 22. So, and diffuse intergalactic medium, both the space between galaxies, it is even less. So the diffuse interstellar medium is very, very rare, but still a lot of beautiful things are going on. That space. Yes. Yeah. Yes. Yeah, it is less stable. When the spins are aligned in this fashion, it is less stable. So the electron spin has to flip to become. Yeah. So see, that is what I told. So there are certain things which are not allowed in spectroscopy. So when you read more about spectroscopy, you will see that there are selection rules for transitions to happen. So this is a kind of transition. You're going from a higher energy level to a lower energy. So this is kind of transition. So any transition to take place, there are selection rules. So like, for example, I don't know, you have learned about vibration spectroscopy, electronic transitions, the what will be the selection rule? It should be 0 plus minus 1. Vibration spectroscopy has some selection rule. So the state, this state is, suppose this is state number n is equal to 2, n is equal to 1. So if the transition take place, delta n will be 1. 2 minus 1 will be, so it is either plus 1 plus or minus 1. It can go from higher to lower or lower to higher. Both are allowed. So if plus minus 1 is allowed, then this transition will take place immediately. The electron is excited, immediately it has to come down. But then there are certain transitions which are not allowed. Okay, so not allowed doesn't mean that it is not going to happen. It is not allowed. It is not impossible. There are certain things which are not allowed, but we do. So that similar fashion, there also, I mean, it is not allowed, but it can take place. Okay, so for example, if you have heard about phosphorescence, anybody knows about what is phosphorescence? So phosphorescence is like transition from, so we can have singlet states, we can have triplet states. I mean, not familiar with. Some of you are familiar with. So a transition from, so singlet state means when singlet state, S, capital S equals to 1 and triplet is 3. Okay. So a transition from within singlet states is allowed. So that gives rise to fluorescence. But from triplet to singlet state, it is not allowed. This is phosphorescence. This is not allowed. But this happens once in a while. It will happen. Okay, but it will take a lot of time. So a transition from higher state to a lower state takes about 10 to the minus 8 seconds. Electronic transition takes only 10 to the minus 8 seconds. If this 10 to the minus 8 second is, it takes few minutes, that means it is not allowed. So this transition is even not allowed. I mean, at the higher level, not allowed. That is why it takes so much of time.
What is this transition, like you said, the transition occurs from singlet to singlet is allowed and triplet to singlet?
No, but this is not. So see, I will talk more about spectroscopy. So we know about 3 kind of transitions: electronic, vibrational, and rotational. This is none of them. Okay, so we cannot. So singlet, triplet, nothing comes here. It is an entirely different kind of transition.
We have selection rules for these as separate.
Yes. So dust. So interstellar medium contains gas and dust. Dust are solid particles and gas. So these solid particles only are about 1% of the total material that is present in the interstellar medium. Okay, this is only about 1%. But 1% itself is too big. And these solid particles can cause interstellar extinction of light, like extinction of tiger. So tiger is, dying. We have very less number of tigers. So light is being removed by the dust particles. The starlight is not coming to us now, not coming to our telescopes. Okay. So what dust is doing? Dust can either scatter it or absorb it. Okay. So scatter is a general word. So scattering means it can reflect the light, refraction can happen, reflection can happen, all kind of things can happen. Okay, and absorption means it can absorb the light and then release that light at different wavelengths. So at different wavelength means mostly at higher wavelengths. So that means it changes the color of the light. And if it is releasing a longer wavelength light, that means that light is reddened. It doesn't mean that it is allowing red light. I mean, any longer wavelength light is a reddened light. So this is what happens. I mean, generally we know that our sky is blue. Why the sky is blue? Because blue light is scattered more compared to the red light of the sun. So blue light is scattered, and we see that the sky is blue. And that scattering, why is that scattering taking place? That scattering is taking place because of the particles that are present in the Earth's atmosphere. Okay, so blue light. So this is Rayleigh scattering, simple Rayleigh scattering. Similar kind of scattering can take place in the interstellar medium. Okay, so we have starlight, the blue light By blue light, I mean the shorter wavelength light. Okay, it doesn't mean that it is of blue color, blue wavelength. No, it means shorter wavelength light will be scattered more compared to the longer wavelength light. Okay, so the longer wavelength light can easily pass through, and we can receive it at our telescopes. But these will be, so this is extinction. So blue light or the shorter wavelength light will suffer more extinction compared to the longer wavelength light. Okay, so and another thing to note is distant stars will appear more redder because the light from farther away stars will be traveling through more of the interstellar medium compared to the nearby stars. So their light will be more reddened. Okay, so in this way we can actually estimate their distances plus how much material is present within. And astronomers who do who study stars and those kind of things, actually they hate this the presence of interstellar medium. Why? Because every time they are looking at a star, they get the starlight, and then they have to do this correction, which is an extra work for them. So you get light from the stars, you want to study the stars, the properties of star, but then you have to do this correction. This is very important correction because whatever light we are receiving may not be the correct light. Okay, so you perform this correction, you remove the extinction part, and then you get the correct light, and then you can analyze your star. But people who are studying this medium, I mean, they are very happy that okay, the extinction is going on, and so this is what happens. We have a star. This star, if you receive light directly from the star, then you get a black body curve kind of thing. But if this light passes through some dense cloud where there are dust particles and molecules can cause this absorption of light at certain wavelengths, and the dust will cause extinction. Okay, and then when you receive this light, then you have to have this correction has to be done in order to understand this correction, in order to understand this protostar, or you can study this light itself, only the extinction part to understand, or the absorption things to understand what material is present in that dense cloud. Okay, and talking about telescopes, so we can have infrared telescopes on Earth. There was Sophia, which I think it's not working anymore. So this was a collaboration between US and Germany, where they had a very nice telescope flying on a plane, but I don't think this is working anymore. ISO is gone. ISO was launched, I think, in 1996. It worked. And then came Spitzer. Spitzer was launched in 2000 something, early 2000. And again, it is dead. Now we have JWST, James Webb Space Telescope, which again works in the IR. Okay, so that is giving good results. So dust, I've already told, it is only 1% of the material that is present in the interstellar medium, but it contributes to about 30% of the flux. 30% of the flux of any galaxy, I mean, in the IR region, at the longer wavelengths. The shorter wavelengths are mostly coming from star-like objects. Okay, but dust, when it absorbs the shorter wavelength light, will emit at higher, longer wavelengths. At the longer wavelength light, 30% of the longer wavelength light, it is typically coming from dust particles. Large grains, I will show examples where large dust grains, they provide surface for chemical reactions. So a lot of complex reactions can happen on surface of dust grains. So how do we know that these dust particles are present? They can interact with the starlight, or they can emit. The dust grains can emit also. So they can interact. What does interaction means? Interaction means they can extinct the starlight. The absorption and scattering can take place. They can reflect the starlight. They can polarize the starlight. So polarization is another very important phenomena. How does polarization take place? So these dust particles will contain a lot of electrons, and there will be some arrangement So if the dust particle is completely spherical, if it is completely spherical, then the arrangement is so symmetric that if some starlight interacts with that dust particle, it won't be polarized. Okay, but generally these dust particles are not completely spherical. I mean, they should not be completely spherical. I mean, there is no symmetry. Why? Because the starlight will just keep destroying them. The surfaces will be destroyed, and so they are not, because they are not symmetric. So they will generally polarize when the starlight interacts with these kind of non-symmetric dust particles. The starlight will be polarized. So and how these dust particles are arranged, because they are non-symmetric. So the magnetic field which is present in the interstellar space, that will actually contribute to the arrangement of the dust particles in the interstellar space. When the starlight interacts with these kind of dust particles, uh, that part will be, those photons will be polarized. So you can attach a polarimeter with your telescope and you can study this kind of light also. So it will help not only in understanding the dust particle but also the magnetic field which is present in space. Okay. Yes.
What's the origin of magnetic solar space?
See, origin, maybe, I mean, several.
So the dust particles.
Yeah, dust particles. I mean, they are charged. They contain charges. So that is one contribution. But there will be more contributions. So not only dust particles, there will be ions, there will be electrons moving, and then there will be, I don't know, maybe some kind of, I don't know if stellar contribution will be there or not, but mostly it will be from ions, from charged particles that are moving, and these dust particles are also, they contain charges in some arrangement of charges is there. So these all, so there is very, I mean, the magnetic field in the interstellar space is very weak if you compare it with, say, the magnetic field, the sun or any star. So this will be very, very weak, but then it does affect the arrangements in the interstellar space. so this this is all interaction with starlight. Then comes emission. So we can have thermal emission from dust grains. When it absorbs the starlight, it gets heated up. The dust particle gets heated up, and then it will emit in the current. Okay, and then we can use the black body temperature of the dust grain to, I mean, black body curve of the dust grain to estimate the temperature of the dust particles. Then we can also have molecular emissions. I will talk about large molecules today, PHs and C60. And we can also have radio emissions from rotating grains. So this is a typical dust particle. See, it has a core, it has a mantle. Mantle provides surface for reactions to take place. The core can be graphite or silicate. Graphite is mostly carbon based, and silicate is silicon oxide with iron and several other elements. So the core can be like that, and then it has an ice coating. Temperature is very less, typically 10 to 20, and less than about 50 Kelvin. So ice can be water ice, can be carbon dioxide ice, it can be methane ice. So the ice is not only water ice; it can be ice of other molecules as well. Okay, and you can see the dust particle is typically a micron size of micron size. So this, you see, what is the effect of dust? You can see the light which is getting scattered from dust which is surrounding stars. So you can see how the halo is forming behind stars. So coming to extinction. So this is A. We denote the absolute extinction by capital A. So A lambda means we are now trying to understand the extinction at a particular lambda, particular wavelength. So this is what happens. I0 lambda is the intrinsic intensity of the light emitted by the stars, and I lambda is the light that is being received by the telescope. We take the ratio, then it gives us the amount of photons that we have lost. So this is absolute extinction. This is known as reddening. This is reddening. So reddening means how much shorter wavelength light is lost. Okay. So this is typically AB minus AB. So I mean, magnitudes everybody knows. So B minus V minus V minus V naught. So this is observed B minus V. B, so you have to measure what? You have to measure the magnitude into B, blue wavelength and visible wavelength, minus the intrinsic blue and visible wavelength light. Okay, so this is typical reddening. This is just number which is ratio of the absolute extinction over reddening. AB over EB minus V. So absolute extinction over reddening. This is a typical number. This number is related to the size of the dust particles. Okay, so larger the size, this number will be larger. Smaller size, this number. So if the size of the particles is small, RV will be small. If the size of the particles is large, RV will be large. Okay. For very large grains, RV is okay. So you can see this. So this is flux, this is wavelength. So flux of an unreddened stars means that there is no extinction taking place for this particular curve. So we get a curve like this. For a reddened star, the light of which is getting extincted, we get a curve like this. So what you can see, what you can note here is that at shorter wavelength, there is a large difference. Shorter wavelength, the extinction is more. Okay, and as we go to longer wavelength, the extinction keeps reducing, and at some point, this both the curves will merge. Okay, so at very large wavelengths, for example, radio. So at if you are working in radio astronomy, for example, you don't need to worry about extinction there. Okay, so if you are using radio telescopes, because there is no extinction or very insignificant amount of extinction taking place at very long wavelengths. Okay, so you are, that particular correction that we are doing in visible and UV wavelengths, we don't need to do at those wavelengths.
Okay.
Yes.
So how do we determine
I know. Okay, I'll tell you. So this is a typical extinction curve for various, sight lines in our Milky Way, where you can see how the RVs vary. So RV is less for this curve, and then it keeps increasing. Okay, so that this tells us that the grain size is increasing. So when the grain size, and it is plotted, I mean on the x-axis it is not lambda, it is 1 over lambda. Please note that this is 1 over lambda. So 1 over lambda means what? That when we are going from 0 to positive x side, this is shorter wavelength, this is longer wavelength now. Okay, so longer wavelength, everything is merged because there's hardly any extinction. But when we go to shorter wavelengths, from here somewhere UV starts, and this is far UV. So we can see that in the far UV there is a lot of difference between these sight lines. Okay, because the extinction is, huge amount of extinction for big, RV when the RV is large because the grain size is increased. Okay.
So
yes.
What does the bump there?
There's a bump. So I naught, coming to I naught. So there are two methods to determine extinction. One is the pair method, another one is multi-band photometry. So the pair method is where you have to have a pair of stars. So we have the target star in which we are interested, and we collect the light from that target star, and then we have to have a standard star. Now this standard star will have to be of the same spectral type and about the same distance as well. So the light from the standard star is unextincted. That means the light from the standard star is I naught because it is of same spectral type and about the same distance. So we can take that light as I naught, and this light from our target star will be I. So this is one way of measuring I naught. Okay. The other way is because we know our target star, we know what spectral type, what is the temperature. So how much photons it should be emitting in a particular wavelength, we already have this. Theoretically, we can calculate this. So theoretically, we can get an idea of I naught. Theoretically, we can also produce I naught. So one, we can produce I naught observationally, and the other way is to theoretically produce I naught, and then we can compare it with the observed data, and then we can measure the extinction along our target star. Okay, so this is a very beautiful extension curve where extension curve have been plotted for SL. One is small Magellanic Cloud, and then we have LMC, the Large Magellanic Cloud, and this purple thing is the see the behavior of the extension curve for LMC and Milky Way is similar. It tells us that the the dust almost similar. If you look at the SMC curve, we don't see any bump, and you have a very sharp rise in the far UV. Okay, so we don't see a bump. It tells us that the particles, the molecules, whatever is causing the bump is absent in SMC. Okay, but the particles, the material that is causing extinction at these wavelengths in the far UV is present more in the SMC. Okay, so SMC metallicity is lower compared to our Milky Way. Okay, so that is why SMC is a very interesting galaxy to study because the metallicity is lower. So that means the amount of heavier elements is less compared to our Milky Way. So, so in what kind of galaxies we can find the metallicity to be low? I mean, any idea? The galaxies with young galaxies, the galaxies that have not evolved much. Okay, and SMC is a nearby galaxy, and it seems that it is. I mean, it is not a young galaxy, but it behaves like a young galaxy. So, if you want to study a young galaxy, you cannot do it because that young galaxy will be so far off. But this is like a lab which is close to us, and we can study this lab, this SMC, get an idea of what kind of material may be present in young galaxies. So that is why SMC is quite interesting to study. SMC. So the bump, yes. So this is the bump. The bump is at 2175 angstrom, okay? 217.5 nanometers. It is very well studied. This bump is very well studied. People have tried to correlate the strength of the bump with the amount of extinction and with the amount of there are other features I'll tell you about. So they have tried to study this bump in various ways. Okay? Now there is a general understanding that this bump is being caused by carbon like large, it is so broad, it's quite broad. Okay, so that broad means that it is being caused by some particle which is big in size. So, and the general idea is that those particles have to be carbon based. So a general understanding is that the bump is being caused by graphite like particles, graphite sheets. So, but it is not clear why this bump is being caused. People have studied the variation in the bump, the variation in the strength of the bump, but one thing which is very the stable, I mean, the bump is always at 2175. There is hardly any variation in the wavelength of the bump. Another features are the diffuse interstellar bands. Okay, so people have tried to study the correlation of this bump with the diffuse interstellar bands. So what are diffuse interstellar bands? Diffuse interstellar bands are again features. They are absorption features. They are quite broad absorption features present on the interstellar extension curve. Okay, where they are present? They are present in the mostly in the visible part of the electromagnetic spectrum. Some of these features are also found in the near IR part of the electromagnetic spectrum. There is nothing in the ultraviolet, or maybe there is something in the ultraviolet, but the ultraviolet part of the electromagnetic spectrum is very crowded. So we don't know whether dips are present there or not. But definitely, and these days, about 500 diffuse bands have been identified. So diffuse bands are absorption features. They don't belong to stars. They are not due to dust grains, solid particles. Because polarization studies have been done on these diffuse bands, and it has been seen that these bands are not polarized. So anything because of the dust particle will show some kind of polarization. It has also been seen that because 500 dips have been identified, it has been seen that some of the dips correlate with each. So if you compare two dips at two different wavelengths, sometimes they correlate. The strength of one is increasing, the other one is also increasing. The strength of one is going down, the other one is going down. And several sightlines, these studies have been done. Only two features have been identified with a large molecule. Only two features have been identified with a large molecule, and others have not been identified. There are several proposals, several molecules have bing suggested, but a clear-cut identification has not been done. So you can see this is a particular 6s14 div. The div at 6s14 angstrom. Here, very high resolution spectroscopy has been done, and what they have seen is they see that this div has rotational structures. There are structures here. You can see it is not a single smooth line. There are structures in this absorption feature. If there are rotational structures, it actually tells us that these dips are not coming. I mean, the carriers of the dips are not tiny molecules, but they have to be large molecules. Large molecules actually show this kind of structures, rotational structures, in that the dips, because they fall in the visible part of the electromagnetic spectrum, that means it is mostly due to the electronic transition going on in the molecules. Okay, so electronic transition and rotational levels are also involved. If the rotational levels are also involved, then only these rotational structures will be seen, and these kind of structures have been seen only in large molecules. Then other features include silicates. So silicates actually show two features, one at around 10 microns and the other one at 18 microns. So we can see absorption features at 10 micron and 18 micron. There is another feature which is present at 3.4 micron, which is generally due to aliphatic stretching mode, aliphatic hydrocarbons. And then there are ice features. So yeah, so dust grains. So dust grains play a very important, as I've already told, they can play a very important role in formation of complex molecules. So what can happen is molecules, because this is micron size, it provides a large surface for molecules to get absorbed, or atoms also to get absorbed on the surface, and these atoms can travel along the surface, and then they can react with something else on the surface and evaporate off the dust particle, and so molecule formation takes place on the dust surface. So you can see all kind of complex molecules can be formed. We can have water, methanol, PH molecules. PH are basically benzene rings, fused benzene rings. We can have, so this is our dust particle, which is a silicate grain. We have this ice coating, and then a lot of molecule formation is taking place. It is even speculated that we can have quinones, and these quinones can further react and form proteins and DNA and so on. So it is speculated that this life-giving molecules may have been formed in the interstellar space, and then they came on the Earth, and then life originated on the Earth. So Stardust mission, there was a Stardust mission of NASA which collected particles from a comet, and it brought back to the Earth. And those particles were analyzed for what kind of solid particles and molecules were present there, and a lot of things. I mean, there's a whole science issue on the results of these. So coming to interstellar molecules now, so about 270 molecules have been detected. There is a database you can go through. All these molecules have been detected using spectroscopy. Mostly rotational spectroscopy has been used because rotational gives you correct information about the exact molecule that is present, while you don't get this exact information using vibrational spectroscopy. First molecule to be detected was CH radical. Most of the molecules are carbon based. So you can see, so this is electronic transition. So electronic transition mostly happens in the visible part of the visible and UV part of the electromagnetic spectrum. Then we have vibrational transitions. So vibrational transitions mostly in the mid IR, and we have rotational transitions. Rotational transitions take place in the microwave region of the electromagnetic spectrum. Thing to understand is the pure rotational spectra that we get. We can get pure rotational spectra only from molecules that have dipole. They should have a permanent dipole. Okay, I am not talking about the rotational structure that we saw in the dips. That is a structure. That is not a pure rotational spectra. Okay, that was an electronic transition, and it had some rotational structure in that. Okay, so that is a different thing. The pure rotational spectra will be coming only from molecules that have permanent dipole. So most of the molecules that have been detected in the interstellar medium they do have this dipole actually. Some of the molecules have been detected using vibration transitions. So vibration is basically vibration of bonds. So if we have CO2, for example, CO2 is very symmetric. So we can have bond stretching, CO stretching of the bond, bending of the bond. These are vibrations. So this is I have not put all the molecules, short list. Important thing here, you can see the detection of cyanobenzene, which took place in 2021, and cyanonaphthalene, which I'll be talking about. Cyanobenzene and cyanonaphthalene. So naphthalene is what? You have benzene and you have another benzene fused together. So that is naphthalene. Okay. Naphthalene is the first member of PAH family, polycyclic aromatic hydrocarbon molecules. So we can add several of benzene rings everywhere. Okay, and we can create a large pH molecule. Okay, but naphthalene is the first member of the pH family, and this was the first pH molecule to be detected in interstellar space. It is not a pure pH molecule, it has a CN. So one of the hydrogen is removed, replaced by CN. Okay, so cyanonaphthalene has a permanent dipole, and that is why it has been detected. Okay, so this we already have again the cosmic cycle. This on. We also know about this, lot of reactions taking place. Yeah. So what kind of reactions can take place on the surface of the dust particle? So see, hydrogen formation of molecular hydrogen is a very, very important phenomena that takes place on the surfaces of dust. Now, people have tried to measure the abundance of molecular hydrogen. Okay, what they found was, and then they tried to create a mechanism for the formation of molecular hydrogen. Okay, through reaction. So what they found was gas phase reactions are unable to produce the kind of abundance that has already been seen in the interstellar medium. So they had to come up with an alternative arrangement, and that alternative arrangement was that molecular hydrogen formation can take place. Most of the molecular hydrogen should take place on the surface of dust grains. So what can happen is, on the surface of the dust grain, we can have accretion. Accretion means hydrogen atoms coming and sitting getting absorbed on the surface of dust grain, and then they can move on the surface of the dust. Okay, so they can, if they have enough energy, then they can hop. There will be barriers on the surfaces, okay, of the dust grain. So if they have enough energy, they can hop and come closer to another hydrogen atom. Or if they don't have enough energy, they can tunnel through this, and then they can come close to the hydrogen atom. and these two hydrogen atoms can react. Okay, these two hydrogen atoms can react, and the energy released in the reaction will help them to evaporate from the dust particle. And so, in that fashion, molecular hydrogen will be formed and will be present in the interstellar space. The dust particle also helps in the survival of these molecules. So, if UV radiation is coming from this side, we have molecules, hydrogen molecules sitting all over the dust particles. The side which is exposed to UV radiation, there the hydrogen molecule will be destroyed. But this one is safe. So, the dust particle is keeping it safe also. So, it is providing two kind of things. One is formation, and another one is protection. Now coming to large molecules. So large, I'll be talking about two different large molecules. So yesterday we had a question how fullerene was detected in interstellar space. So we'll consider that first, and then I'll go to polycyclic aromatic hydrocarbon molecules. This is another large molecule. You can see this is basically fused benzene rings. So fullerene, how fullerene has been detected. So first time fullerene was detected in space using Spitzer data in 2010 by Jan Candy. This paper was published in Science. So I'm talking only about C60, which is pink in color. So this one, you have to focus on this emission. So there is emission at about 19 microns and 17.4 microns. So this is the 17.4 micron line, this is the 19 micron line, and we also have 7 micron emission line at 7 micron and about 8.5 micron. So there are 4 different emission lines that have been detected in a planetary nebula, and this is coming from fullerene C60. So how these lines are created? These lines are in the mid-IR part of the electromagnetic spectrum. So mid-IR means it is because of the vibrations that are being caused on the, in the fullerene molecule. Okay, so we have two different kinds of modes. So the 19 micron and the 17.4 micron is due to radial motion of the carbon atoms. So fullerene is like a ball, football. So radial motion means this kind of vibration. The ball should increase in size and compress. This, okay. So the bonds will increase so that it increases in size. It will be a three-dimensional increase in size and compress. So this is one mode of vibration which gives rise to these two features. And then there are modes due to tangential vibrations. So we have the surface. So we have bonds, carbon bonds. These bonds will be increasing and decreasing like this. So on the surface, it will be like tangential motion. This was radial motion. This is tangential motion. Okay. So this tangential motion is giving rise to these two features. Okay. So in order to identify, so suppose you are looking at some particular nebula, in interstellar medium, and you are able to identify, okay, we have seen this 18.97 micron, 19 micron feature we have seen. Okay, and then you can say, oh, we have discovered C60 in this particular region. No, this is not possible. Because C60, if it is showing one vibrational mode, it has to show all of the vibrational modes. So all of the vibrational modes should be seen collectively, okay, together. Then only you can say that it is fullerene. Because fullerene has what? CC bonds. Basically, it has CC bonds. And all these vibrations are due to CC bonds. Now, CC bonds are present everywhere. CC bonds can be anywhere. CC bond is there in ethane also. It may not lie, the vibration in ethane, the CC bond vibration in ethane may not be at 19 micron, but there may be some molecule which has CC bond vibration at 19 micron. But it won't have all the vibrations. It won't have vibrations at, suppose, 17 micron and 8 micron and 7 micron. This is not possible. So if you see all the 4 features together, okay, then you can say that, okay, we have identified C60 molecule in space. Okay, so this is neutral C60 identified in space and C70 as well. in a planetary nebula. Important thing is that spectral lines of pHs are absent. So this planetary nebula is what? Planetary nebula, I've already shown there is a star, white dwarf formation is going on. There's a white dwarf sitting at the center, which is very hot. And then there is a lot of gas, which is expanding away from the star. So we have different regions. We have regions that are close to the star. We have regions that are far off from the star. It has been seen that this C60 has been discovered closer to the star. If you move away from the star, you find pHs also. Okay. But if you go away from the star, the abundance of C60 goes down, the abundance of pHs goes up. Okay. But if you move closer to the star, the abundance of C60 goes up, while the abundance of pHs goes down. Now C60 doesn't have any hydrogen. C60 doesn't have. pHs have a lot of hydrogens. Okay. So it means that the region where C60 has been detected is a hydrogen deficient region. There is scarcity of hydrogen there. Okay. So this is Jan Lemy holding his keyboard. He is a professor in University of Western Ontario, Canada. Divs. Now C60 is again related to divs. So I've already told that 400-500 divs have been identified. Only 2 of them have been directly related to a particular molecule. Okay. So that is why I came again on this. So this is the extinction curve again. And dips are here somewhere in the visible and near IR part of the spectrum. These are absorption features. 2 of them have been identified. See, so this is all the dotted things that you see are lab data. The black line is fitting of that lab data. This lab experiment was done in Switzerland, and what they did was they took the gas phase spectra of C60 plus ion, fullerene cation. 1 electron was removed. Okay, and in gas phase, because C60 or C60 plus, if it is present in interstellar space, it is present in form of gas. It is not a solid particle. Okay, it is present in form of gas. So we have to record gas phase spectra. Gas phase spectra at very low temperatures, and we have to try to make it, at as much vacuum as possible, very low densities also. So this kind of experiment is very, very difficult, but they did in Switzerland. They recorded, and these two, the red lines are diffuse bands in the IR, and they got a perfect match. So again, this was published in Nature. So you can see they got. So this was the first direct matching of a carrier of diffuse interstellar band. So, but only 2 of them. And we have like 400, 500 diffuse bands. So I don't know how many molecules you need to identify all of it. But at least this is the beginning, and 2 of them were identified. How C60 formation can take place in interstellar space. So it is not understood first of all. So if you have a hydrocarbon, for example, like for example wood is a hydrocarbon, or paper, you burn it, you get what? You get amorphous carbon, black soot kind of thing. The soot contains what? The soot, if you analyze the soot, you will get what? You'll get C60, you'll get pHs, you'll get amorphous carbon, you'll get carbon clusters, everything you'll get, lot of things. Okay. Now, people have tried to understand this. What they have done is they have burned hydrocarbons in labs, and they have tried to see what is going on, but it burns so quickly that the reactions that goes on is very, very difficult to understand, to see. So you can always give a theoretical pathway. You cannot analyze it experimentally. So people have, scientists, even chemists A lot of chemistry is involved. So chemists have actually speculated and they have given theoretical mechanisms for formation of C16 pHs, soup particles, but it is not clear. But this is one idea how it can be formed. So we have C60. We start with pH molecule having 60 carbons and hydrogens on the edges. All these are hydrogens on the edges. Let's see. Then what happens? We start removing the hydrogen. Dehydrogenation starts taking place, and this one is fully dehydrogenated system. After it is dehydrogenated, why hydrogen is being removed? Because if pH processing takes place, the CH bond is the easiest to break. So first CH bonds will break, then only we can come to breaking up CC bonds. Okay, so all the hydrogens are removed, and then CC bond starts breaking and carbon removal takes place. When one carbon is removed, because it's a benzene ring, it contains 6 carbon. One carbon is removed, so only 5 carbon remains, and they form a pentagon kind of structure. So if you look at the football carefully, we have a pentagon, and on all the bonds of the pentagon, benzene rings are there. And then those benzene rings are shared by another pentagon. So we have pentagon, benzene rings, this benzene ring, again pentagon, again benzene ring. So pentagon helps in the curling up, the curvature. pH molecules are flat, you can see here. These are flat, they are not curved. But in order to form C16, we need curvature. This curvature comes only when we have formation of these pentagons. Okay, so when the pentagon starts forming, then ultimately it will form C16. And this is one speculation. It's a short movie. Yes. So this is what is happening actually. A lot of these pentagons are being formed, it is curling up, and then ultimately it goes on and forms C16. Now coming to pHs, very quickly in the last 5 minutes. So pHs, I mean, my favorite molecule because this is where I do most of my research. So these are benzene rings, let's see. They can be formed anywhere. Okay, I mean, you are driving a scooter, the exhaust of the scooter will contain pHs. You're smoking, the fume will contain pHs. Everywhere, they are so ubiquitous. They are very carcinogenic. They can cause skin cancer, they can cause lung cancer. Lot of very difficult to handle also, we have to handle. Now, why do we want to study pHs? Because we have unidentified infrared, now they are identified, I should say. We have infrared emission bands. Okay, these bands, these are the infrared emission bands. They lie at about 3 point, they are in the mid IR. So they are coming due to the vibrations in pH molecules. They lie at 3.3 micron, 6.2, 7.7, 8.6, 11.2, and several weak features. Then there is this bump, which is speculated to be coming from graphite kind of particle. Graphite is what? Carbon based. I mean, if you increase the pH molecule size, it becomes graphene. And then you stack up the graphite. Okay, so maybe pH is contributing to the 2L75. Then we also have an extended red emission, which is found in some objects, some interstellar objects, which is like a big bump here in the visible part of the, and diffuse bands again. So because diffuse bands, 2 diffuse bands have already been identified with C60 plus, and it is also speculated that diffuse band, C60 is being formed by the help of pHs. So maybe pHs are also contributing to diffuse bands, but identification has not been done yet. Because pH molecule is not a single molecule, as I've already shown here. See, pH molecule is a family of molecules. You can create n number of molecules. And all these n number of molecules will give rise to these emission bands. Okay, because the emission bands are coming due to vibration of CH and CC bonds. And all the pH molecules will have similar kind of CH and CC bonds. Because there is similar kind of CH and CC bonds, So CH stretch will always give rise to the same feature, whether it is a small pH molecule or whether it is a large pH molecule. Okay, there may be very tiny shifting, or maybe the intensity will vary, but nothing else. So I've already told that we have infrared emission bands. The strong ones at 3.3, 6.2, 7.7, 8.6, and 11.2. How emission takes place? So pH molecule can absorb the UV photon, which is coming from a star, and they emit IR. So this is what happens. Suppose we have a pH cation. Cation will have doublet states. So these are electronic states. D0, D1, D2 are electronic states. These smaller ones, smaller horizontal lines are vibration states. So when it absorbs a UV photon, it can go to a higher electronic state and a higher vibration state. And internal conversion can lead to a higher vibration state of the ground electronic state, and then it emits IR photon. There is a cascade of emission. It doesn't come directly one by one step by step. It comes down emitting IR photons. So a lot of IR photons will be emitted, and then it comes to the ground state. You can see this is CH stretch. CH stretch. CH bond is vibrating. Here, this is CC stretch. CC, combination of CC stretch and CH in plane bending. The CH is vibrating like this, and the CC bonds are also vibrating. And this is CH out of plane bending. CH out of plane, pH molecules are planar molecules, and there is a CH, and this goes out of plane. So that is CH out of plane bending. So if we ionize pH molecules, then what happens? We can see that a neutral is there is a neutral spectra. Neutral spectra will have very large CH stretching and CH out of plane. Okay, while the ionized pH molecules will have a lot of features in between. These features are coming because of CC stretching, CC vibrations. Okay, so in neutrals we have more CH vibrations. In ionized pHs we have more CC vibrations. This I think I'll skip what is the mechanism. But there we can see a lot of variations in the pH spectrum. So very slight variation. You have to have high resolution spectroscopy to observe that. So you can see here the 6.2 micron band feature. If you see, it is here lying at about 6.2, and then there is a red shifting taking place. So it can go from 6.2 to 6.3 if we observe in different sight lines. And same thing can happen to the 7.7 and 8.6 micron feature. I don't want to go into details. Why the shifting can take place? This shifting can take place because there are structural variations in the pH system. A lot of different kind of pH molecules can exist. We can substitute one of the carbon atoms with, say, nitrogen, oxygen, or something like that. Then pHs can also have side chains. Okay, so this is one example where nitrogen is being substituted. So if you remove this carbon and substitute it with a nitrogen atom, so this is pure pH cation, and you get this. This is 6.2 micron feature. Okay, so you get the feature here, which is redshifted. I mean, the 6.2 micron feature is at 6.2 micron. It can vary from 6.2 to 6.3 micron. Okay, but how do we explain it? So the 6.3 micron may be coming from a pure pH molecule. If we start substituting the carbon atoms, and if we go deep inside the pH molecule, there's a blue shift scheme. So this one is exactly at 6.2 micron, and this one is at 6.3 micron. So we can explain this by substituting nitrogen at various positions inside pH molecules. I think I don't want to go into my research. Nothing else, but I'll show you the rotational. So I told you when I showed the molecules discovered. So cyanobenzene and cyanonaphthalene have been discovered in 2021, and because they have a CN, so they show rotational transitions, and the discovery was made in the microwave region using rotation features. So what we did, we theoretically calculated the spectra of cyanobenzene and cyanonaphthalene, and we found an excellent match with the experimental spectra. Maximum error of 1% was there. Okay, and based on this, we have now predicted the spectra of these molecules and substituted coronine. This is a coronine pH and CN attached coronine, and we have predicted these lines should be observed so that observers can go and search for these lines, and detection of cyanocoronine or nitrogenated coronine may be possible. I think this is a picture which shows we have a carbon rich star, and as it evolves, it throws out a lot of material, and then there is formation of molecules taking place in its late type phase, where we have simple molecules, complex molecules, we have pHs, we have carbon nanotubes, we have fullerenes, we have all kind of, and these, I mean, you can see we have oxygen, we have carbon, we have nitrogen, various elements are there in these molecules. So interstellar space actually is, it's a vivid lab, it's a very rich lab where molecule formation, complex chemistry is going on. It is very, very difficult to produce though that kind of chemistry in laboratory, but theoretically people have, even our group, we are trying to match the abundances of molecules present by using models. So these models require a lot of reactions. Okay, so we feed the reactions into the model, and then the model actually tells us the behavior, how a molecule, the abundance of a particular molecule will vary with time. So it will increase or decrease, or it will saturate or something like that. So these modeling studies are also there. So I think I will stop here. Thank you very much. I will take questions if yeah, yes. So you have to compare. So you know the star. If it is a O-type star, for example, you know the spectral type of star. Once you know spectral type of the star, then you know its black body curve, and then you know how much photons will be emitted in a particular wavelength range. Okay, and then you compare it with what we're getting observation. So if you are getting less, that means some part is lost. If you're not getting less, then it is not existing. So you have spectral type, you can plot a black body curve. So then you can determine the temperature and you can get an idea. And spectral type also can be determined using spectroscopy. So what kind of ion? Suppose we have ionized helium, for example. Ionized helium dominates in O-type stars. Hydrogen dominates in A-type stars. So if you do spectroscopy also, then also you can determine, you get an estimate. So you have to do several kind of estimates to determine exactly the spectral type, and then using that. Any questions online? No? Okay. Thank you very much.
Recording stopped.
Passing to ISSAA,
Yeah.
would be very but this also like this documentary
So see, extinction studies are very local kind of studies. This redshift which you are talking about is a large scale.